All right, before we get started here, I've got some embedded videos in here too, I'm going to show, but yeah, YouTube is kind of frowned lately on people just sharing, downloading and sharing. So I'm going to try to link directly to them. When these videos come up, if there's problems with bandwidth issues and it stutters a lot, let me know and I'll switch and use the embedded ones instead. But I'll try to respect their opinions as we go along. The other thing here, this is going to be a hard act to follow. I looked and saw that W3LPO was one of the previous showers, and I don't know if I can follow in Frank's footsteps here, but we'll give it a shot. My presentations are, sometimes people say they're good and they got a lot out of it. Other times, more experienced hams say they're a little bit simplistic. I try to target an intermediate level and introduce it for a beginner too. So hopefully it'll be something you get out of here. But if you're looking for some fantastic new insight in how to run a balun, and you've been doing these things for years and years and years, I regret to say you're probably not going to get a lot out of it, but hopefully something new will pop into this. Over the years, people have said that about baluns and common mode chokes, these things that are on your screen, and if you look at them like things got worse after I added a balun, or you really ought to have one, or just use a couple turns of coax and things, or I burned up my balun. I didn't really know what the heck baluns did. Did I really need one? Some people said yes, some people said no. So I started looking, what exactly do I have to do to make a balun work, and do I even need to work with one? And after I got into contesting and all these people kept whipping me, I sat down and I'd pick a topic and start researching it. And this was one of the ones that I came up with, and I decided to document some of the things as I went along. So that's what got me started into this. What's going on with the baluns? Let's see here. Ferrite Common Mode Chokes is what we're talking about. And I'm Kevan, N4XL. As we said, been licensed since 1975. Extra, probably about 3 years after that, 2-3 years after that. But it's not that I knew a heck of a lot about stuff that got into the multiple guests, and I was able to work my way through it. When I started looking into the baluns, one of the first things I ran across was this from Roy Llewellyn, W7EL. Some of you may recognize him as being the grandfather, pretty much, of the development of ham radio baluns and chokes. And he says, I've always been a bit bothered by baluns since I was never sure what they're supposed to do, let alone how they might go about doing it. And I thought, well, I'm in good company if he doesn't understand or didn't one time know how they work. We're going to be looking at an overview of why ferrite and common mode chokes should be used in your shack, describe how to effectively use them. And this isn't going to be a how to build. Pretty much we're looking for, you can get that stuff off the internet, but we're going to take a look at some of the theory and why there's so much confusion about how these things work and whether you need them or not. Start out pretty basic. For common mode talk, what we're going to be talking about is it's the unwanted current that flows on the outer surface of the coax shield. And if you take a good look at that coax, because of surface effect, that braid operates like a two-sided conductor. The signal will flow on the inside of that braid close to the dielectric and the inner conductor, and then common mode current will be flowing back down on the outside of the braid, opposite directions at the same time, and it can happen because of the skin effect on it. And when you look at the junction that occurs between coax and a dipole, let me find a pointer here a minute. This section right up here can create an imbalance, and that current flows up and it ends up coming right back down on the outside of the coax. And that's where that unequal current begins to come from. You can also get that unbalancing effect, not just because of that junction, by running your feed line off in a different direction and creating an asymmetric pattern on each side of the dipole. And because that feeder line runs closer to one side of the antenna than the other, it's setting up conditions where you can have imbalance and start getting common mode current. Just as all the electrical wiring and things inside of the house will cause an unbalance in that antenna, making common mode currents worse too. One of the first things I heard about these things was that you needed a balun, a common mode choke, up at a Yagi because it'll distort the radiation pattern. And I ran across this drawing as I went going through things. A guy did an easy neck uh, modeling of it. And in fact, you do see a distortion of the Yagi pattern off to one side, and it traditionally evidently destroys some of the front to back ratio on a Yagi. So it does have a difference. But in my mind, that's not the major type of issue associated with a common mode choke. And for that, turn to YouTube, and there's a discussion here by IZ2UUF. Let me see if I can make this link work. At this point, if this starts stuttering, somebody speak up and let me know. And the volume's not adjusted, let me know as well. This will be about 3 minutes.
Often, ham radio operators debate whether a one-to-one balun is needed on resonant dipoles or not. To test the effect of a balun on a resonant dipole, I built a dipole for the 40 meters bend with a switch that can bypass the balun. The first test is the measurement of the VSWR. As we can see, the curves, with balun or without balun, are almost identical. There is no way to see the balun effect with the VSWR meter. Now we shall perform a radiation test. A transmitter will be keyed, while the balun will be alternatively inserted or bypassed. An RF emitter will monitor the amount of power radiated by the coaxial cable. Another RF emitter will monitor the power radiated by the power cord. We can now key up our transmitter. When the balun is disabled, a significant amount of power is radiated by the feed line. Without balun, even the power cord radiates. The paddle cord also radiates. Electric shocks can be perceived when touching the base. In this test, we shall use a signal generator to simulate a source of noise nearby the coaxial cable. Such sources of noise, like switching power supplies and others, can be met by the coaxial cable along its path within the house. So, let's turn on our signal generator. The injected note is very evident when the balun is disabled. The lack of a balun has no significant effect on VSWR. However, it causes significant radiation from the feed line and other wires. It might cause higher noise due to feed line pickup. Thank you for watching.
So in a nutshell, what you're looking at with some of these baluns isn't so much that you get a bad distortion of your Yagi pattern, although that is somewhat disturbing. The more pressing issue is the noise that you'll be picking up on that line and the interference you'll be causing yourself. In addition to that, give an example of when I first started as a ham, my novice license, I had an inverted V on the top of our 2-story house, and it ran from the peak of the roof about a foot off the top of the roof down to the ground. And I didn't know anything about that being bad. Heck, I had an antenna up and could have some fun. But because of that, I was getting a tremendous amount of common mode current flowing down that coax into the radio. Plus, I had a ham shack up on the 2nd story, and I was trying to run a ground wire down to the ground. and that set up some configurations where I would get a little bit of tingling shock from that key whenever I'd mess up and touch it because of the different things. So a bail-in might have helped me out a little bit in those conditions. So even though you can't see the effect with an SWR meter, it's probably a good idea to have a bail-in in. Now he mentioned about feed line loss and that, or feed line radiation. Here's some different types of coax shielding. You can see they have different dB shielding requirements based on whether it's a single or double shield. A lot of beginning hams think RG58 or 8 is perfectly fine to run, but notice the minus 55 dB compared to something like LM400, which has greater than 90 dB shielding. The better the shielding is, the less radiation should be coming from those coax feed lines, and that will generate noise in your shack as well. As a practical example, I'm not very good at it, but I run a single operator 2 radio setup here when I'm doing contesting, and I had a jumper cable go bad and between my filter and one of the radios one time. So I looked around, and the only thing I had handy real quick was some RG58, and I ran a little jumper to replace some better quality cable between it, and I definitely started picking up increased noise simply because of the shielding on that cable is the only thing that had been changed, and that caused me some problems. So when we got done with the contest, I swapped it out. So it does make a difference, and if doing mobile trailer operations or things, you might look at a little bit better high quality cable. Having said that, I follow or subscribe to Jim Brown, K9YC's philosophy about things and grounding and bonding, and a lot of his presentation here, we'll be talking about him a little bit later on. He has this to say as well: shielded cable rarely solves RFI problems, probably because to do anything useful, cable shielding must be continuous with the equipment shielding. Lots of equipment to which you'd like to connect it is unshielded. And we'll give a couple examples about that here in a minute or two, but he's basically saying is if you've got your nice high quality shielded coax and you think you're reducing your radiation from it, that's all well and good from the coax, but what you connect it to is in some cases just not bonded or grounded correctly. And so that wonderful shield that you paid all the extra money for the cable isn't doing you any good whatsoever. And well, before I leave this part of it, take a good close look up at the braid. And if you notice, there's a lot of parallel conductors running in that braid. And just note at this point, and it'll become an issue later on, that with those parallel conductors going like that, that braid has a capacitive reactance associated with it. Jim talks a lot about a pin 1 problem, and I had no idea about it until just a few years ago. That it was really causing problems in the radio. And since I've started addressing some of his bonding methods, I've cut down significantly on things in the shack. But it's surprising that a lot of people still don't know exactly what's going on in this, their radios in their station because of a pin 1 problem. So what is it? Well, here's a nice Elecraft K2 transceiver. And if you look down at the mic and the headphone connectors down there, they're not actually grounded to the casing of the rig itself. And that's kind of what we're talking about, Jim, was with the grounding coax cable not necessarily bonded correctly inside of your shack. And they do that, according to Jim, so that you can easily remove the casing and not have to worry about all these connections to the different cables and things. You can easily pull everything off. But the problem with that is it's not connected, grounded, bonded to the casing. So it sets up a condition, even though it's going through the chassis of the radio to the ground wire, that is the very condition which can cause your RF signal, common mode currents, to be injected right into your equipment, be it a radio or whatever the case may be. And how that works is he had this nice drawing on his website which shows the right way to bond something inside of the radio if it was designed correctly on the right hand side, where it's grounded right directly or bonded directly to the casing. But in just about every case we have of every piece of equipment in our shack, it's really set up the wrong way, which is on the left. That outside braid of the coax, for example, or could be an audio cable ground, goes into the radio itself. And although it's bonded to the chassis, you end up getting a path of like going from points 1 to 2 and getting current to flow through all that inductance and resistance that's in that flow path on the inside of the radio. And if you got current flow through these impedances through that path, you're going to end up getting a voltage developed across those things, and that can help cause that common mode current to go right up into the inside of your signal circuitry and start causing RFI. So the whole concept here for a common mode choke is to go ahead and put a big impedance on the outside of the radio, which will reduce the voltages on the inside of the radio, and that should cut down on a lot of the RFI. And that's what happens in the case of a common mode choke, that you put it out there on the braid or coax coming in from the antenna. Hopefully you'll develop the voltage from that common mode current on that balun or choke outside of the radio and not have much energy left to go up into the signal circuitry at the end. That's what the basic pin 1 problem is all about. And he didn't discover this. It's not limited to coax. He was actually an audio engineer, and he was doing a concert, and he started noticing a lot of the problems he was having was from common mode currents on his audio cables. And that's what he started doing research, and he figured out that that happens a lot on the coax as well. And if you think you're not susceptible to it, we just showed the Elecraft, but here's a Carver stereo. A lot of us are old timers. If you're into audio at all, that's a pretty recognizable name from back when we were a little bit younger and had hair. But if you look, there's little rubber insulating rings around these connectors. So even though you were taught to use shielded audio cable, it wasn't shielded or ground bonded to the casing of this high dollar audio equipment. Same thing with our laptops that we use today. You plug the cables into them, and that path goes right through the inside of the laptop before it gets to the ground connection you might have associated with your computer. And then W8JI, a lot of you ought to recognize his name, Tom Roush. He and evidently Jim Brown were talking, and they discussed this. They took a look at their Astron power supply, and you think you can connect on that little ground lug that's right there on the back of your Astron, but they opened it up and they took a look inside, and on the inside where the other side of that ground lug bolt is, they had a painted connection on the inside of the Astron, so they weren't getting a very good ground right there, and that kind of messes you up. That's kind of a safety concern. I had to pull mine open and take a look to see if I had some problems, and mine was painted too, so I took a little sandpaper out, sanded it off. You got an Astron, you might check that part of it out. Any questions before I go on here a minute? Okay, I've got another video here, and this one is about ferrite in general. We haven't quite got into the common mode choke aspect of it yet. And I think this takes, if I remember right, about 13 minutes or so. But I found it pretty interesting exactly what the heck ferrite does. Let's see if we can make this one work.
This video is going to talk about ferrite beads and kind of some of the filter applications for ferrite beads. There's lots of other applications for inductors and RF toroids and transformers and such, but we're just going to talk mainly about the filter applications for ferrite beads. And a lot of different forms. A lot of times you'll see these large kind of split core beads that you can put on wires to reduce interference and provide some filtering. In fact, if you look at a lot of the computer cables that you have hooking into your computer, like the USB cables, like this one for my mouse, and that's basically a ferrite bead sitting under there. And we're going to talk about what job it does there. You'll also see sometimes, just simple little cores like these guys here. Maybe they'll have multiple holes in them, to make like a transformer or a winding, like this one here, making like a little bit of an inductor, or just a simple bead on a wire. Okay. And how do these work? The ferrite material is a high permeability material, so it makes it easy to get larger value inductors when you make a winding out of them. But also, at higher frequencies, they introduce loss. And what that means is that at high frequencies, they essentially start to look like resistors. Okay, so they're not really ideal inductors anymore. They really just look more and more resistive. Okay, and so in other words, they basically add loss at higher frequencies. And sounds like a nice thing when it comes to doing filtering. And just to kind of show you the effect of that, I've got a simple little setup here. My signal generator is set up to do a sweep, let's see, from 10 kilohertz to 40 megahertz. Okay, and I've got this going into this little block down here that has, basically the signal coming in, going through this wire, coming back out again, and then up into the scope. And I've got the scope set to look at that, that's the whole sweep. So essentially the signal that's here, okay, is running at 10 kilohertz, and then it's sweeping all the way up to 40 megahertz at the other end. Okay, so if we put some frequency dependent device in series, right here, we're going to see that effect on the scope. So in fact, what I can do is if I reach over here and grab one of these ferrites, I'm just going to grab one that's easy for me to deal with in my hand. So it's got 2 holes in it, but I'm only going to use one. Okay, and if I kind of pull this wire off of here, slip this ferrite on there, okay, and let's see if I can get this thing to kind of jam its way back in there and stay in place. Okay, so now that that ferrite is just on the wire, I didn't do anything else other than put the ferrite on the wire. Let's look at the scope. We can actually see that the response now, at 10 kilohertz is really not affected, but I get out to about 20 megahertz here, and I've lost some amplitude. I go out, and you can see it's kind of flattening out. But with doing nothing more than slipping this ferrite on the wire, I've introduced some loss, and that's mainly because that's essentially a series resistor at those frequencies. In fact, if you add more cores, it just gets better. So if I take and open this guy up, throw another core on here, okay, and see if I can make that guy stick. And now I look at the scope. Now I can see by the time I get to the middle of the screen, which is about 20 megahertz, I'm down about half the signal amplitude, or in this case that would be 1/4, less than half the power, 6 dB down, right? So just by slipping some ferrite cores on there. Now if you take and put some windings through a core like this one here, that makes it a lot more effective. Okay, in fact, if we take and bridge this guy across here, look at how effective that thing is. So at low frequencies it's passing just fine, but as soon as we get up to a few megahertz or so, I can see that it's really introduced a lot of loss. So that's a pretty effective filter for high frequencies. Okay, so another way to think about that is, it's really kind of restricting, the high frequency content. And so that's one common use area is for like EMI suppression. And that's one of the reasons why you'd find them like on computer cables. You got some high-speed signals going through some of these computer cables. And if you've watched my video where I talked about the frequency content of square waves, you will know that the faster the rising and falling edges, the higher the frequency content you have. So let's look at that same effect and how the ferrites will affect the high frequency edges or the high speed edges of signals. So I'll switch my signal generator over here to a square wave that's continuous. Okay, let me connect up my wire here again. And if we go to the scope and kind of speed this up here, I can see, let's turn the brightness down to the scope here. Okay, so I can see some really pretty fast edges on this square wave here. In fact, so fast I can't really see them. Okay, in fact, it's got about 2 nanosecond edges if I kind of speed the scope way up. There's 5 nanoseconds of division. You can see it's less than a division, so it's a really fast edge. Okay, and if I take, let's take just as an example that multi-turn, ferrite here, and if I connect that up here, look at the resulting square wave. You can see that it's really just taken all the edges, right out of it and filtered them away, kind of making it almost look, closer to sinusoidal. So what it's really done is remove that high frequency energy from that particular signal. So you can actually see, that it's would help to maybe reduce the radiation of that high frequency coming off the wire and interfering with radios and other things like that. So that's a very common use case, is for EMI suppression. Also, another good use case would be for like improved power supply decoupling. Here's just a little schematic example. Maybe I've got an IC here. I've got some local decoupling here. Sticking a ferrite bead in series with the power supply coming in, what that will do is two things. One is, if there's any high frequency energy being generated in this chip and it wants to come leak out the power supply, the decoupling cap can short it to ground. But if this ferrite bead wasn't there, it might also propagate out onto the power supply plane. Okay, so what this does is ensures that this capacitor looks like a lower impedance than the rest of the power supply plane, and it makes it more efficient. Also, similarly, beads can also block higher frequency energy from coming in through the supply, okay, as well. So typically used for some power supply decoupling. It may also be used for controlling parasitic oscillation. Okay, those of you that may remember a video that I did about a year ago, where we talked about this circuit here. Let me kind of move over it. And the concept in the video was talking about analog oscilloscope bandwidth considerations, meaning how much bandwidth do you need in your scope to measure, whether you're working on audio signals or whatever. And I built this little circuit here, which is a simple audio oscillator. This oscillates at about 2.5 kilohertz or so. But it also had a parasitic oscillation in it. And so if we kind of switch the scope over to look at that, I've got the circuit built up right here. And if I switch my scope over to look at this, okay, let's kind of get this kind of going here. All right. So you may remember some of these waveforms if you looked at that video. I'll put a link to it in the notes there below the video. And what we're looking at is the base and collector voltages of this circuit down here. So I'm looking at the base right here and the collector voltage here. So the collector, we're just seeing that oscillation, or the regular sinusoidal oscillation as intended. On the base, we're seeing this thing burst into a high frequency oscillation, here and here. And the point of the previous video, to talk about bandwidth, was that if the bandwidth of the scope was less, like 20 megahertz, I wouldn't see that oscillation where it really is there if I go to full bandwidth. So I talked about a way to kind of get rid of that oscillation. And when you're dealing with bipolar transistors, it's often necessary to have some lossy impedance in at least 2 of the 3 nodes. And in this case, I really only have it in 1. And what I did in that previous video is I added a little bit of resistance in series with the base, an actual physical resistor. But the same thing can be accomplished with the ferrite bead. Okay, so very easy to see the oscillations here. If I come down and look at the circuit, okay, there's the circuit built up on the board. I'm using a simple 2N2222 transistor right here. Okay, and then here's my capacitors and the resistors and such. So I've got a ferrite bead just laying here. If I pick this transistor up, okay, and I'm going to go slip that ferrite bead over the base and slide it back in. Okay, now with that on the base there, without doing anything else, that oscillation is now completely gone. Everything is nice and clean. Because essentially what's happened is by putting that ferrite bead, right here in the base, I've introduced some loss at that very high frequency. This thing was oscillating at about 200 megahertz. So now at 200 megahertz, there's this lossy element in here, adding some delay and reducing that signal amplitude, that 200 megahertz signal amplitude, to the point where it doesn't induce an oscillation anymore in there. So sometimes you'll see circuits that have got ferrite beads, sitting on a lead, and that is most likely why, is just to suppress, some parasitic oscillation like that. So that's another kind of important application. Also, to reduce RF coupling, from circuits. I mean, if you're designing like an audio amplifier for a microphone that goes into an RF transmitter, you might use some ferrite beads on the power supplies and on the audio lines to keep the RF signal from coupling back into the amplifier itself. Now, there are different material types. Sometimes they're called the mixes. And these different mixes are good for different frequency ranges. So you'll see mixes like 43, 31, 77. There's a whole series of numbers. and each of these mixes are good for particular frequency ranges. So what you probably want to do is kind of look at some of the more popular manufacturers, like Ferrite is one, Fair-Right, Ferrite, Amidon, Murata. There's several other manufacturers, but they've got a lot of application information about, which mixes or which material mixes are suitable for various frequencies that you might be operating with. So you may want to consult some of their website material as well. So anyway, I hope this was a good introduction to what ferrites are and some of the applications of where they can be used for EMI suppression, like limiting the speed of some edges that so they don't radiate a lot of energy, improve some power supply decoupling, control parasitic oscillation, etc. So, of course, any questions, let me know. But again, this is just intended to be just a little bit of an introduction to the topic. And thanks for watching.
I had always kind of wondered what the beads were that were on just a regular piece of wire. What the heck that stuff was up there for. That kind of explained it to me a little bit. I appreciated him telling you that. These are the clip-on things, which all of us ought to have a handful of back and around the shack. And you take and you wrap them through the ferrite bead. I used to just do one or two of these wraps through that thing. But then I figured out that I need to really put as many as I possibly can through there so that I can snap that thing shut. And I've seen people actually kind of run tape or something on the outside of them, but you really need to have those plastic clips there snap in place so that the ferrite surfaces, flat surfaces, are as close and smooth together as possible to make that ferrite core work correctly. And don't, if you can't snap it together, I'd go ahead and use a different type of ferrite or use another one, throw that thing out and get yourself a good one. One thing to note of here also, we mentioned about capacitive reactance before, is if you take and you make a coil of wire out of this thing, you're going to have inductive reactance associated with that too. And as I said, we'll talk about that in a little bit. Here's some practical examples of how ferrite's used. For those of you who are wondering a little bit about commercial, I've had a lot of people tell me that this Balin Designs is one of the better balins and common mode chokes that is available out there. So you might consider them pretty strongly. I've had good luck with DX Engineering, but a lot of people I respect have said the Balin Designs is an excellent piece of equipment to use. And they've got different kinds. A two-stage one for verticals and inverted L's seems to work really well. A feed line choke, you can make them yourself pretty much just by slipping some of this ferrite over the coax, then got some heat shrink tubing or some electrical tape there to hold it in place. And if you think that's not quite good enough, you can actually go out and spend money on these types of feed line chokes in these tubes. But if you open it up, that was one of them went bad on me. So I cracked it open and took a look. And that's really all they do is you go out and spend money for somebody to slide a bunch of ferrite over the top of your coax. You could have done it yourself for a heck of a lot cheaper probably than going out and buying one of those types of things. You can make these out of PVC yourself, run a couple wires. So something to consider, easily to do. Here's a DX Engineering. I actually used this for a while. I had a 520-foot horizontal loop up, and this is a 4-to-1 version from DX Engineering. And it worked really well for me for a long period of time. As I mentioned at the beginning, I just run 100 watts. And a lot of people call me crazy for getting something that does 5 kilowatts. Why in the heck would I do that if I've only got a 100-watt transistor, or excuse me, 100-watt transmitter? But we'll get into that a little bit towards the end too. And also take note that there's regular wire on the inside of this, not coax. It seems to be preferred by some of the people that you use some Teflon wire or some type of coax like RG400, which will not heat up and cause migration on the inside of the coax, which happens if you take some of the coax and you loop it around a core and it starts heating up. You're setting up the conditions to allow that center conductor to start migrating through the dielectric and changing configuration of the cable. So most of the people now that I've run across lately are recommending you not use that coiled coax method anymore. Use some just regular THN wire. There's some other types out there too, and use that. But like we've been talking about before, here you've got wires that are coiled and in parallel. And that's going to set up a resonant frequency on the inside of this choke or balun. And that can cause some problems if it's not installed correctly. So the goal of a common mode choke is to set up that high impedance on the outside of your signal circuitry, but how much is high? What do you really need? A lot of people think that 1500 ohms is perfectly fine, and that's what they strive for. But most people who run particularly high power stations or seem to have a lot of smarts about them say that you really ought to have greater than 5,000 watts, especially with a high power. And I took that to heart, and I went ahead and bought me that 5 kilowatt balun I told about a minute ago. But I also ran across a couple places that said even with 100 watts, the minimum you should use for a balun is a 3,000 watt balun. So we'll start seeing some data from Palomar Engineering a little bit later and make you kind of understand why that's the case. So 5,000 is what a lot of people strive for on this. Some of the things I've talked with about people, they know that the mix makes a difference. These two charts give you an idea of why. I chose them because basically what this has is at 10 megahertz on both of these materials. This is a 43 mix, that's a 61 mix, 10 megahertz, and you go up to the curve for 2 turns. With a 61, you're only getting 60 ohms of impedance with 2 turns, but with a 43 mix at 10 megahertz, you're getting 200 ohms of impedance. And you can see the curves are shaped a little bit different. And you can download these for each individual type of mix and figure it out for yourself what it is and what your range is likely to be for that particular mix. You can't just throw something in there and expect it to work just fine. You got to be aware of some of these different factors. There's a man, I think he's a silent key now, G3TXQ, who come up with some charts. And as I started looking at them and I dug into this a bit, it occurred to me that just like antennas, a choke will work best when it's used at or near the frequency it was designed for. And G3TXQ says you need to choose a choke which has a high impedance and is resistive over the frequency range of interest. Not just a high impedance, but you want to have it resistive as well. This K9YC, he says he's kind of enamored with number 31 material, saying it's a problem solver, and it was developed about 2004. And what he's saying is it covers a range of component values between 1.5 and 150 megahertz, which a lot of us on HF and DX, and that covers most of what we want to do. 31 would be a good mix. And the reason why he says that is a single choke on number 31 material can be made to provide very good suppression over about an 8-to-1 frequency span, as opposed to a 4-to-1 for number 43. That may or may not be true. I don't really have the smarts to evaluate it, I hate to say, but we see a couple things that are contradictory to that in a minute or two. But he's been spot on enough. I decided I would take him up on his observations and measurements that he did. Here's a chart which shows a couple of things comparing number 73 and 43 material. And on this chart, you see that there are the resistive curves and the reactance curves. And as the reactance frequency goes up, it goes down and you hit basically a zero reactance. So the choke is entirely resistive at that particular point. And then it goes from inductive down to a capacitive reactance. So it changes over from a resonance point in the common mode. And you can see that the different materials have their resonant point. One of them, this is in the HF band, and this is in the VHF band. So different materials will have different resonance frequencies, is why that's important. So if you go out and you decide to buy a balun, or common mode choke and throw it in there, and you didn't take the time to figure out where is its resonant frequency most likely to be, and you see that it doesn't work for you at all, or you end up making things a little bit worse, you may have got hold of a device that has the improper ferrite mix for your particular application. And this just shows that your target range is to have zero reactants at those particular points. G3TXQ made this chart back in 2012, and we'll take a look at a couple close things, but essentially this shows the greens, the darker the green, the more impedance it has. And he sets up things here for like 12 turns on RG48 on a FT240 core made of 43 material. And we'll zoom in a little bit more. And this black bar represents the portion of the frequency range over which that particular balun is resistive, mostly resistive, as compared to reactive. So if you're designing your station and you're going to throw a balun in, you would want to use the particular design in that black range as much as possible, rather than getting outside of it. And he also has these color codes to tell you what's good and what's bad. And here he broke out what those color codes are. The light green's greater than 4,000. The dark green is greater than 8,000 ohms impedance for those particular ranges. Excuse me. And as you look at that, you go along this chart, you start seeing, for example, that 8 turns, you get a very wide banded resistance section to it, but it only goes up to maybe 2K ohms of impedance with 8 turns on a 240 core of number 43 of coax RG58. If you go up to 12 turns, you narrow down the resistive property and you start getting more impedance, but your bandwidth starts going down accordingly. So as you add more and more turns, you get more impedance, but it's designed for less of a bandwidth. Now, at the beginning, I talked about some of the old timers used to tell me just coil up a coil of coax and about the size of a bleach bottle, and you can make yourself a good RF choke. And if you look down here on his chart, he's talking RG58, not RG8 in this case, but you got to have 10 turns, 15 turns, 20 turns, and it's got a very limited range of application for high impedance values. So you have to know about how many turns and where you're trying to use your common mode choke at will determine what your coils are. If you don't have any choice and you are using an air cored one and you're not getting any relief, this will tell you that the lower in frequency are, the more turns you have to have. But notice there aren't any resistive bars anywhere, black bars anywhere in that section. So there are better choices to make than just coiling up some coax, because any type of coax you make out of this just coiled up coax is going to be a resistive, or excuse me, a reactive type of balun, and that's not desirable. In fact, in his charts, if you're trying to find, if you're having some problems with common mode on 80 meters, there isn't a single coil of coax that will really give very much impedance at all for an 80 meters. And I had a guy question me, and the first time I gave this, he says, "Are you saying that a coiled up coax won't work at all?" Well, yeah, it will work. It'll give you some impedance. It's just not very much, and maybe enough for your particular situation, but not guaranteed. If you're looking for something for 80 meters, you're far better off choosing something up here in this section to reduce some of your common mode currents. And that works vice versa too. You don't want to use one of these type of things if you get interference up on 10 meters. So good idea to look this over and figure it out. But again, most of the people these days are not recommending you use the coax wrapped around the core. And we already talked about that. Reactive chokes have the disadvantage that they can resonate with a common mode impedance path that's also reactive, but of the opposite sign. In some cases, that coupling can actually increase the common mode current flow rather than choking it. And what that's saying is you might have a remember that braid had capacitive reactance associated with it. Well, if you've got a choke that actually is inductive reactance, the inductive reactance will cancel out some of the capacitive reactance, and that'll just drive up your common mode current in some case, unless there's a resistive component to your device as well. Here he explains that a little bit. He says, take the example of a 20-meter half-wave dipole. It's put up about 30 feet above the ground and feed it with RG213, and it drops straight down from the dipole. And when he put this into easy neck, I think he said it was, he found that he had about 0.17 amps of 1 amp applied going back down the outside of the coax, giving him some common mode current under that configuration. And then he went ahead and he threw in a common mode choke that had enough inductive reactance in it to exactly cancel out the capacitive reactance of the braid. And all of a sudden, instead of that 0.17 amps, EasyNex said you're going to have 0.64 amps. In other words, more current that's going up to the antenna is going to be coming right back down as common mode current than actually is being radiated by your antenna. And that's not a good scenario to have happen. Started out with 0.17 amps, and if you actually put in a resistive choke of only 200 ohms, you end up getting an increased reduction of common mode current over the other device, which is a reactive choke. So that's one reason why you want to make sure you have a resistive rather than a reactive choke on the inside of there. Now, there are problems with resistive chokes, though. Here's some thermal images of a ferrite core, coax wrapped around it. And he's got a low permeability core and a high permeability core, and he put 100 watts on them for 5 minutes and did a thermal IR image. You can see the one on the left, which was more of a low permeability core, generates a lot of heat. And that can be a significant problem. And that's partially why you end up causing valence to fail, is if you don't have enough resistance after you get rid of that inductive capacitive reactance in the device, you can start getting severe overheating on the inside. And you can also cause problems with just the reactive loads as well, cause such heating to occur. And as that core heats up, of course, the heat is going to begin to start attacking the wires that you have around the device, or could actually cause the ferrite core itself to break down. I've opened them up before and seen the ferrite crumbling apart because it wasn't designed to handle it. G3TXQ says that for high power applications, RG400 can be used in place of RG58. It seems to do much better in the heat conditions with little change to choke impedances. And we already mentioned about RG58 and the shielding capabilities of it. K9YC has some general rules for valence and chokes. Obviously, more impedance is better. And all ferrite chokes should be designed to operate in the frequency range where they have a large resistance, but reactance is small. We pretty well kind of talked about that several times. And that's conditions are satisfied at or near the choke's resonant frequency. And again, the designed plans for these things are out on the web. But if you're thinking about substituting materials or deviating from the plans, these are some of the things that can happen, and you ought to be aware of those choices before you start making those decisions. Jim also has a cookbook out there about how to make these valence. I strongly encourage you to go ahead and read them. He's got 2 out there, a new choke cookbook. If you just Google K9YC cookbook, you'll come up with this particular device, and he likes his number 31 material, like we said, and he uses these 2.4-inch OD toroids and a 4-inch OD toroid that you can get. And when you Google K9YC cookbook, if you come up with this old one, which he no longer recommends you use, that's the one that has just the RG8, 11, 8X, and all that stuff coiled around on things. But you can look at it and see he breaks it out by 160 or 80 meters, 30 meters. These are just some examples that I pulled out of his old cookbook. And it gives you a rough idea how to make them and what type of design was good for that. But again, you can get some problems when you start wrapping coax around these devices and they start heating up. So he come up with a new cookbook that he put out a year, a couple, 3 years back, 2017, I think, but I'm not sure. And in this, you can see he doesn't list coax anymore. And we exchanged a couple emails, and he said, be sure to tell him not to wrap coax around a ferrite core. So I'm passing along his wishes. You know, Teflon or THHN wire, he tells you how many turn chokes, and he breaks it down into exactly how much impedance you're getting. And again, what the bands are. So armed with that information, it's really not too hard to rule your own type of ferrite choke if you actually want to do it. And this breaks it out so you'll know what you're getting when you get done with it in the end. Sometimes or other, old timers, which most of us are, know that if you go out and you get a high SWR at your antenna, a good SWR at your antenna, but it's high in the shack, that you might have some type of problem with common mode chokes. Sometimes people will tell you if you can't get a match on your tuner to just go ahead and change the length of your feed line. And that does work, but it doesn't solve your common mode current problem. And if you do end up in a situation like that, I've seen it here in my own personal shack sometime. I get a good reading at the antenna, but where my external SWR meter shows that I've got a higher in SWR than I do out at the feed point of the antenna. And then I look at the SWR bridge in the transmitter itself, and going into a dummy load, they read pretty close to each other. So I know the calibration is pretty similar, but the external antenna reads significantly different from the internal SWR meter. Tells me I pretty much can figure I've got some type of common mode choke, or excuse me, common mode current causing me a problem. And I could add or subtract some feed line to make all the problems go away at the transmitter, but it doesn't stop a lot of that radiation problem or noise pickup problem that's occurring on the feed line. So that's not the ideal solution, just inserting or removing coax. You want to tackle the common mode current issue itself. And in fact, G3TXQ talked about that. As we vary the length of the coax, the braid path impedance changes. And when the coax is close to a quarter wave along the common mode path, it's a high impedance, relatively little current flows along the braid. And that happens whether we include a choke or not, because we're at that quarter wavelength point and there's no current flow at that point. When it's close to a half wavelength long, though, substantial current flow is happening at that halfway point, and if we don't include a choke. But there's no length of coax where an unlucky reactive choke impedance could not work against that braid impedance and make things worse. So if you break that down, you look at the statements, what I took away from this is the first part implies where you put a choke in the feed line can affect how well it works. Putting one right at the feed point is a very good thing to do. I also put one right at my shack as it comes into the shack on my 160 meter inverted L, because although I've got a buried feed line out there from my inverted L to the shack, 160 meter signals penetrate down into the ground and goes right into the braid of that coax. And even though I'm stopping the current right there at the feed point of the antenna, I'm got a chance I'm picking some up even though the coax is buried. So I put another one right on the input to my shack. And I actually got one of the RadioWorks transformer, isolation transformers is what they call it, that happens, that have a copper strap at the input of the line isolator. And then I tie that copper strap right to ground. So any common mode current that's flowing on the braid of that coax, much rather go right straight to a ground rod than try to make it up through that line isolator impedance and get into my radio. So I've got two on the line going from my verticals out there. The second half of this statement basically says, don't use reactive chokes if you can avoid it at all. Here's what they're talking about the coax. This purple line represents current. And at the quarter wave point, you have no problem whatsoever. So the whole timers, as you move and adjust your coax by changing its length, you can find that sweet spot and not cause a problem. But if you connect it, you're getting all kinds of problems. You might be near to a half wavelength of the antenna. But if you're running a multi-band antenna, you've got multi-current paths in there, and there isn't a single place you can put your transmitter that you're going to be guaranteed to be at the quarter or half wavelength set point. So again, it's best to try to solve the common mode issue rather than just trying to guess what particular length to put it in to your system. And G3TXQ mentions that for a multiband system, there's potential, if you're using a reactive choke, that on at least one band, you're going to have the choke putting in there, if it's reactive, will exacerbate the problem and make your RFI and your noise pickup much worse if you're doing a multi-band antenna. So it makes sense to try to use monobanders if you can. Now, we've talked a lot about transmitting. Tom's got a great website talks about, and he's real big into receiving antennas, as many of you know. And he mentions he uses 73 material for his receiving applications and low power applications between 0.1 and 30 megahertz. And I thought I'd mention that. He talks also that if you choose your material in your core design so that a downward slope in permeability is happening with an increasing frequency, it helps control the impedance in his broadband transformers. So if you roll on your own, you might like that little tidbit. And I threw it in there for some of the more advanced people to, if they weren't aware of that, to think about it and to encourage them to go look over Tom's site. Because if you're trying to roll your own, little tidbits like that will save you a lot of time and trouble and design issues. Because you're not going to pick that information up out of K9YC's cookbook. The stuff is scattered all over the internet, and everybody's got a little bit different take on things. Tom also says where K9YC like to use number 31 material. Tom says for high power applications at HF, it's often necessary. Hello?
We were outside. That was nice.
Tom says that it's good to use lower permeability, which has a lower loss tangent and higher Curie temperature. It handles heat better. Materials like 65, 61 work better for him, he's found, and he's a pretty respectable guy, Mr. 160 operation. Or he even uses 43 materials over 31. So he's got some good, powerful reasons, and that means Jim isn't always correct as well, or maybe Tom's out to lunch and Jim's wrong. You pay your money and take your choices. But that's part of why I got into this, and so many people are confused, is respectable people have different opinions. Now, I read that loss tangent, and I had no clue what that meant, so I had to look it up. And this came out of the internet from a science website. Loss tangents related in a complicated way to the proportion of the peak stored energy dissipated as heat during the charge and discharge cycle. So Tom's saying that if you're using this thing in a high power application, a material that has a lower loss tangent will dissipate heat much better, and you've got less chance of that balun failing under heavy use. Tom also goes on and says, we often assume heat means a core is very lossy or saturating, but that's not often true. He says, if you basically, you got to consider the power level, duty cycle, and the last is the next part we're going to talk about, the ability of the core to dissipate heat. You got to look at the whole picture. He says these very small cores, like the one just slide over the coax, like in the bead type baluns. Remember, I had opened one up and showed you what was on the inside of it. They can only dissipate a fraction of a watt in open air. Well, if you take these bead type coaxes in these little PVC things, and they can only dissipate a fraction of a watt in open air, and you put that little resin around the inside of them and then encase them in a tube, you're not giving them a chance to dissipate heat very well. Matter of fact, it's going to concentrate a little bit. That might not be the best design to use in a lousy antenna setup, which we'll mention in a minute, or if you're using high power. Tom basically says even a fraction of a dB loss produces significant heating in those small cores when power levels is in the kilowatt range. We're going to look at some claims of the manufacturer in a minute. It says their balun works at 1500 watts. They're going to be a little critical about their specs. Loss difference, in other words, your insertion loss in non-resident resonant applications between lower and high permeability ferrite cores isn't much different, but the heating can be significantly different between the two of them. Radio works. Some people think they're respectable, some don't, but their website's still up. He's not making his equipment anymore, I don't think. The rated power for his baluns assumes an SWR of less than 2 to 1, and he's not unique in that. Most of the specs out there, when you go look at a balun and you see it's 1500 watts, 5000 watts, so they're assuming a small, low SWR. And what do we use baluns for a lot of times? To stop common mode current on multi-band antennas. And if we're using a tuner to tune like a G5RV, or if we've got a 102 foot, what am I trying to think of? Dipole up there, and we're using a tuner to match it on all bands, we're not going to have a 2 to 1 SWR up there on the output of that balun. But that's what the power rating is based upon, assuming that you do. Duty cycle and CW or sideband with normal processing, he's saying also too. Well, a lot of times people use their antennas for RIDI or FT8 or other digital modes, and Radio Works, when they rate their baluns, they're saying 2 to 1 or less, and using the low duty cycle mode is where they rate them at. You got to think of how you're going to be using that balun. He goes on and he has this, and I've actually seen this in my shack before. When a ferrite core balun saturates, you'll notice an upward drift in SWR long before the balun fails. Core saturation can be caused by too great a mismatch at the load, or by running too much power, or a combination of both. You see an upward movement in SWR, locate the problem immediately. If you got to keep operating, like you're gonna got to get through that contest or make that DX through the pileup, you must stay on the air, drop your power a little bit until the SWR drift stops down, then go figure it out later on what's going on. Palomar Engineering has this chart, and on it you can see they have some different ratings. Here's a D rating factor. Full power rating is SSB for them, 50% on and off duty cycle. I never thought about it a lot, but they're saying if you use heavy processing, you need to derate their baluns and core chokes by 75% of what they're capable of. That's the same thing as a CW with a 50% on and off duty cycle. You're doing continuous carrier work, 50% on and off, goes down a little bit lower, and for continuous carrier like digital or AM or FM, you're down to 31% of what they rate their devices at. So if you're going here to buy yourself a 5,000 watt balun and you think, oh, I'm plenty well covered, if you're doing digital operations, that thing's only good for about 1,563 watts. If you're doing heavy processing, you get down to 3,750. And again, this is at about a low SWR. They don't specifically say, but I'm going to assume it's somewhere around 2 or 3 to 1 like they did before. And that means if you're using a multi-band antenna again with a high power tuner out there, you better get a balun that's pretty hefty to be able to handle 1,000 kilowatt or 1,500 watts coming out of this thing. And in fact, 100 watt transmitter, I read on a couple sites, I don't know if it's true or not, but they're saying under some high SWR conditions, you ought to have yourself a 3,000 watt device, choke or balun, to keep from having it destroyed by a 100 watt transmitter. So although a lot of people laughed at me and think I'm ridiculous for getting that DX Engineering 5,000 watt balun, I have had problems with baluns that were rated at a kilowatt before that I bought 1,500 watts before. even with my little 100-watt transmitter, but I've never had a problem with that DX Engineering one rated at 5,000 watts. So I'm pretty happy with that operation. I don't mean to trash radio waves here, but I pulled this off the internet a couple days ago for this presentation. Notice that 1-to-1 balun up there is only $29.95, and it says air core tri-filter winding balun is perfect for a basic dipole and 75 ohm balanced to 50 ohm unbalanced connections, rated at 1500 watts. But you start looking at that a little closer, it's only 200 watts CW. What sense does that make? That's only 13% of the full rating. I'm assuming that because it's 13% as compared to Palomar engineers, that they've already taken into consideration that people are going to use this in a multi-band application with high SWRs, but I don't know that for sure. Frankly, I wouldn't trust that balun to perform very long in a bad situation. So just something to think about. A lot of times people wonder what's the difference between a voltage and a current balun. And they say don't use voltage baluns to stop common mode current. There are cases to use voltage baluns, but usually you want to get yourself a current balun, and this was a simple design picture to pull it off the internet. Essentially, a voltage balun is a transformer. This is connected to your transmitter, unbalanced to the balance going out here to your balanced antenna, or you could put these things back and forth in the opposite direction as well. But if you look at that and you think about it, if common mode current is coming along this here and it's going through this transformer windings and common mode current's going there, it's a good chance that that common mode current is going to act like the transformer is going to transfer that to the other side of your balun, and you're going to have essentially common mode current on the other side. Whereas a current balun, you get the stuff going on one side and going on the other. You can wind them such that that magnetic fields created will tend to cancel out any of the common mode current that's occurring on the braid. So that's why most people, if you recommend you use a current type of balun. Another difference thing when to use a balun or an unun. An unun is used a lot when you're using coax to feed a vertical antenna. And just as a quick look, you got one part of it is not grounded and the other part of it is grounded on your load. And then you also determine whether you use the braid or the center conductor, which is connected to what particular point on a balun or an unun. So if you ever try to use a balun to like feed like an inverted L or a vertical antenna, that's not the proper choice to use. You really want to use an unun to be able to cancel out a lot of that information. And I'm not going to go into too much more detail on things. These are just some of the things for you to think about a little bit. I've got a ton of references. I use a lot of K9YC, Palomar Engineering. Comes to their G3TXQ's website, still up and moving around. DJ0P talks a lot about current mode currents as well. Of course, videos we saw. You can't do any research on baluns without talking about Walter Maxwell, W2DU, and the ARL puts out a book for them. Got a couple of them, useful information in there as well. And there's 2 or 3 other things out there. Jim Brown's Choke Cookbook is a great place to go and start reading about that. So that's pretty much my presentation. Do we have any questions? All righty.